Hello. Yes, let's get started with the third part. Basically, uh, understand the mathematics and maybe a little bit more intuition into what deep learning is and why it works and how it works, right? So the last two parts we did a lot of tensor operations. We did understand what autograds are, or what basically it's a way to calculate the gradients for all the variables in your network, right? So you must be thinking, where are we actually going to use it, right? So now I think actual deep learning starts where we will be building some small models. We will trying to build models, and then uh, use our own intuition to build models first, simple models like regression models, and then we will bump it up, use much standard code that are used in any open source projects, right? Hopefully we will be able to do that. Okay, so I have got a notebook, right, and uh, and also a page where I can explain you the mathematics and stuff. So let's get right into it. Okay, so what we're gonna do is we are gonna understand few things about deep learning. I think you already know. I'm assuming you already know what a linear regression is. Okay, for someone who does not, who doesn't have a background in machine learning whatsoever, so basically it's like you have a data set. Okay, you have a data set. Let's say I'm just calling it x and y, right? And you have few points here. Mhm. It can be 2, 3, and 4, 7, 5, 10, something like that. And if you plot it, if you create a scatter plot out of it, you will find something like 1, 2, 3, 4, 5. Okay, it would be much bigger, this one. 1, 2, 4, 4, 5, 6, 7, and whatever. So you plot the scatter plot, one something, the 2 goes to 3 here, and then the 4 goes to 7 here, and something 5 goes to 10 somewhere on the top, right? And so basically you are trying, if you create more points like this, it might come up like this. Okay, some scattered plots points here. Okay, something like that. You are trying to find one line that fits this data. You might say this line actually kind of fits the data. So this is the goal of linear regression, right? So you have some data, assuming it is linear, because that's an assumption that we make, and that's one more assumption, that it comes from a Gaussian normal distribution. Uh, yeah. So apart from the assumptions and all, so you might say that this is a line that fits the data perfectly, and that is what a simple linear regression model would be. So we're gonna do the same thing, but we'll be using the ideas of deep learning as such. Okay. Okay, let's get going. uh so coming to how we're going to approach is, every line, the equation of a line, y is equals to mx plus c. I hope you remember this one from high school. uh, so this is a line which has an intercept, that is the c part. Here is the c part, and the slope of the line would be the m part, right? Okay, so every line can be defined using this equation. All that we need to do is change two things to get the line that we want, right? Now the two things that can be changed is, for example, x and y, and x and y are the data pointers. They are not to be meddled with. You cannot change them, but there are 2 points that you can actually, that's m and then that's c. These 2 points can be changed, and now you have to find this way. So what happens when you change them? So for any line in a plane, let's say this line, if you change the m, you change the slope of it. So it would, if you increase the m, if m is increased, this line will become like this. The point, the intercept point will be the same because c isn't being changed. If you increase it further more, it will become more, like the slope will increase basically. I hope that's clear, right? And secondly, if c is increased, so this is same line, okay, assuming let's remove these two lines. If the c is increased, it just goes up, so the line would be like this, and m is being constant, okay. If you decrease it, it will go down here, right? So if you are increasing both of them at the same time, let's say, if you are in, this is the original line that we have, let's create the new line that we have in different color. So if you are increasing both of them, so it will go something like this, okay. If you are increasing m, if you are, let's say, increasing, m is being increased and c is being decreased from this original line. So if you increase the m and c, then the line would look something like this, okay. I hope that makes sense. So the idea here is to able to find this m and c, so that we get this perfect line that is in the uh, mm, that fits the data, right? Okay, it's cool. Pretty simple stuff. Anyone who has a background in machine learning probably already know this stuff. So what we're gonna do is we're gonna take a simple model of regression, and I'm gonna draw a small computational graph for this one. So you have a neuron right here, okay, and you have data coming in, that is x, and here some operation will happen and you will get the output y. That's all. That's what we're going to do, simple. So this node is what we call a neuron, okay. This is a neuron where actually the computation happens. It's just a representation. So according to this, we also add in some weights. So it's, we multiply these weights with the input, and then we also add in a bias. Bias comes from here, or you can, there are two three ways people denote it. Few people just give an arrow saying it's the bias that comes in, or few people just uh, put the bias right inside it, so it's like this. So the final equation would look something like y equals to plus c, okay. So here the, this omega is playing the role of the slope and b is playing the role of the intercept, okay. And this is what we are gonna get, right? I think this also been shown here, and this epsilon is an error that is basically uh, irreducible error that we don't know in the data set, right? There's always this one error inside data set that we really cannot understand. If you want to read more about it, I suggest the book Statistical Learning. Something I forgot the full name. I will probably write it down. Yes, in the description. So let's start with what we are gonna do. Okay. Now idea is to find the values of this and this, guys, so that the line actually fits the data set. Okay. So first step would be to actually create a data set, right? The first step is to create data set. It's just a demo data set. We're gonna do it. The firstly, we are gonna use NumPy to do all the things. Okay. So this is where we are gonna create data set. So right now, what we have here is pretty okay. So according to the code, we are using b as 1 and omega is, or w, whatever w is actually omega. So it's 2, and the number of samples in the data set is basically 100. Okay, so it's a big data set, like not big considering deep learning, it's very small. You have a x label and a y. So y is the label and x is the independent. So this is the dependent factor, this is the independent factor, and here it comes in. So if you see, we are creating some random numbers Okay, x is some random 100 by 1 data set. This is the size of the data set. If you want to see, I can show you that to you as well. X. So you see, this is the data set. Simply just few numbers. Okay, that's it. And you are adding the epsilon, that is this random noise, into the actual data set that you're putting in. And then you calculate the y. Y is basically this thing that we created right here. So y is, if you see, y is equals to the b plus into what? Into the x plus whatever the epsilon there is. Okay, this is the y. So if you calculate the y, you have the x, and you want to see the y, so it looks like what this. These are also just numbers. Okay, so you got x and you got y. This is the x, this is the y. Cool. So you create a data set. You can, okay, so this is basically, now I'm splitting it into uh, a training and a testing set. We all know we train on a small on a much bigger size, and then validate or test it on a smaller size. Okay, so that's what we are doing here, just shuffling it once. Well, in this example you don't really need shuffling, but in real scenarios the people mostly prefer doing some kind of shuffling to the data set. Okay, so that's what's happening here. You're getting in and shuffling it and then creating. So 80% of the data, that is 80, we have 100 data points, right? So let me just write that here. There are 100 data points, 100. Okay, so 80% is used for training, and then the 20% is used for validation or testing, whatever you call it. Cool. Yes, so let's do that. Okay, and let's just draw the graph, and you see the graph is right here in front of you. So this is the data set that we created. Okay, the training data set is right here in the blue, and the validation set is right here in the red. What we see is that the data points is way too less compared to the training point in validation point, right? So that's something we do. Okay, let's start with actual machine learning, right? We created a data set. I think you understand what data set is. Just a big ass data set of x and y. Okay. Coming to the next point, we have the gradient descent. Okay. Sorry for that. Yes. So now our idea is to find this original value of true b and true w. Okay. We know the actual value is 1 and 2. We want our network or our deep learning network to find this 1 and 2 by approximation. So we all know every network, every deep learning network can approximate a function, right? So you are giving in, the actual functions. Now we want our model to find this b and w. Okay, just using the data set that we have created out of it. Okay, we added few noise too, but so it will never be like exactly 1 and exactly 2, but it will be an approximation that will tend towards 1 and tend towards 2. Okay, as the more the data we train, we will get that actual value. Okay, that's the idea that we're coming up with. Cool. So we are randomly initializing. You can see b is one number, and so basically I guess everybody knows numpy. Okay, so random seed is basically, it's kind of creating a pseudo randomness. So every time whatever values I'm getting here from this random number that's been generated, it will be the same for you also, because we are using the same seed. Okay, so we are getting a number, a random number. That's why this function random.rand n here is basically saying that get me a random number from a normal distribution. So it will always be between -1 and 1, as you can see. Okay, so we print it out. We print out the random numbers that we created. Now we want, so this is the b value, this is the w value. We know the actual b and actual w. Okay, so according to our data, our random initialization. Okay, sorry. Yes, okay. According to a random initialization, the true value, true b is 1 and true w is 2. And according to our initialization, the b is 0.5 and w is minus 0.138 whatever. Okay, and 67. Okay, so this we want our b to go to 1 and w to go to 2. This is the whole idea, and we are going to use deep learning to get to that point. Cool. So the first step is done. The second step is to compute the model prediction. Compute the model prediction is basically the forward propagation. Okay, so now according to the small graph that we created, right, that was this one. There the data is coming in, the x is coming in, and there's a bias coming in, the weight is there, and you get the guy. So according to this equation, y was equals to the b plus omega into x, right? Cool. So you know the b is actually this one. We are using this one as the b. Okay, we're going to use b as this one, and then w will be here, and we're going to calculate the y for every single x. So there are 100 data set for x, right? And so all of them, all these values will be one by one put inside one of them and find the value of y. Then again put inside one of them and find the value of y. So 1 2, so a lot of them will, so 100 of them will be there, right? So this is what we call the forward propagation. You are just passing in all the values of x one by one and calculating what would come out of it, the y. So as you have, according to your data set, right, x, we are using the x train here as we split the actual data set. Okay, just so you can see what x train x split looks like once, so that, so x train looks something like this. There are 100, there's not 100, there's actually just 80 of them. If you can see the shape, see 80 and 1. So basically it's a whole column of 80 rows and all of that. And if you see uh, y train dot shape, it would be 80, right? Cool. And if I check this one, xval or something, it will just be 20. Okay, autocomplete is good. Yeah, so you can see now I'm putting this one here, right? So it has to give y hat will be again 80 by 1 matrix, you can call it, basically a column of 80 rows, right? And you can check how it looks, right? You can see all this answers. Okay, so now this is the prediction of your model. Okay, the y hat here, the y hat is a prediction of your model. Now what do you think would be the last not last, the next step? We do calculate how far away are we from the actual y and the y that was given by the model. So the actual y comes here, right? We took the b as 1 and w as 2, and we calculated same thing here. So if you check here, this was the actual y, right? So if you see in this scenario, this was the actual y. This is the ultimate goal that we have, so that y would be like this, but our y looks something like y hat. This. So you can see there's a lot of difference in the numbers, right, inside them. We are trying to find what is the difference between both of them. So we call it the loss. Loss is basically how far away or what is the error in your prediction of the model and the actual data set, right? So that would be the error or the loss function. Okay, so in simpler ways, just to, if you want to see what is the difference between two different numbers, just subtract them, right? So you see that right here that you get an error is basically y hat and the actual y values that were coming out of it, right? So y hat and the actual value. So if you are taking this is the y, right? So the y hat minus the y train, or you can just call it y also, that's not a big deal, but this would be your error. I hope that makes sense. Just give me a second. Okay, cool. um Coming to the next part. Where was I? Yeah. So the generation is done, and loss function needs to have this way of quantifying the error inside the model and the actual data set, right? That is what it essentially mean. But we are going to reduce the loss, right? There's ultimately we are trying to reduce this loss, the difference between the predicted value and whatever the actual value was in the data set that we created, right? So now this needs the when you are trying to reduce the loss, you are using something called gradient descent. What it essentially mean is you have to create a function of this is also a function, right? But you want a function that can be reduced, the basically it can be differentiated. Okay, so gradient descent is one of those algorithms that helps us do that. Okay, but for that you need the function to be differentiable. Okay, so now the problem with this, there's one problem that you can see here happening is that uh let's say let's say uh this is your original data set. Okay, this is, I'm gonna draw the original from green. 1 2 3 4 5 whatever. Okay, and this is the line that we got. Let's say this is the line that we got or we drew. So what is the, what is the quantified error actually? What is the error in this? This part is the error, right? This part is the error, this part is the error, this part is the error, 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 then again this part. Okay, of course this, let's use one here. So, this is the error. So what is it? The actual data was in green, right? And what you see is our model. So if it was, let's say, an example of the, let's say, uh, number of rooms of a house and the pricing. Okay, so it's saying if the number of rooms was 1, the actual model says the price is somewhere around um, 80K or something. Okay, and but your model says the price is actually only 60K. 60K. So what is the difference? It's basically 20K. And how did you get it? By subtracting the value, the bigger value from the smaller value. Hmm? But that's okay here. You see, in this scenario, in from our equation, what it says is subtract y pred. So here the y pred is 60K, right? So if I subtract 60K minus the 80K, it will give a negative value, right? It will be minus 20K. Okay, keep that in mind. So if this is happening, okay, so this will be, the difference will be minus 20k here in this part, because this is the y pred and this is the actual y for this one. For here, the y pred is this value here. You see the y pred here, right here. This is the y pred and this is the actual y. And here it's okay because the y pred is bigger than the y actual. So in this scenario, it's okay. Here also the limit is 20. Okay. So eventually what you want to do, you want to quantify the error. So you'll take one such thing, one, and you add them all up, right? This all the bluish lines will be added. The difference basically will be added. But if you go on adding this, so example, this one and this one, if you add this, it will just become 0. So does that mean our model has 0 error? No. So to help mitigate this problem, to solve this problem, basically, there can be, what if we just take the absolute value? Okay, we can just take the absolute value of both of this, right? And that will work. This will become the error. But again, think on this one. Okay, if you take the absolute value, yeah, of course, in for this example, this first example that we have, we are getting 20k. Of course, the second example also 20k, and other examples we will all get positive values, and we can add it up and we will get the error. All good, all good. There's no problem with this. Actually, there's no problem with this. But there's one small problem that we have, that is we want to do gradient descent, and gradient descent requires your function to be differentiable, and all of us know for a fact that a modulus function is not differentiable. For a function to be differentiable, there are few conditions. Like the first condition is the function needs to be continuous, right? So if you see the graph of a modulus function, it goes like this, right? This is the y equals to mod of x. Okay, so although it's continuous, but as you can see, there's a point here, and you cannot differentiate a point, right? And secondly, because what is a differentiation? It's basically a tangent to a curve, right? Any curve, you have this tangent, and this will be the value of the differentiation. So you have this, if you have a, this is the curve that you have, so this will have a tangent, right? This is basically the value of differentiation. So a point does not have such a tangent. You cannot draw a tangent to a point. So this function, the function that we created out of just doing the modulus, will not work, because we need to do gradient descent to reduce the loss eventually. So what we do is, there's another easier way to do this, and that is just take the square. You have the value y hat minus y, or y train, what you want to call it. This is actual y. Okay, and you can just square this. This will solve the problem. So if the difference was minus 20, you can take the square of that. That will become, right? Cool. I think that makes a lot of sense. Cool. Yeah. Uh, yes. So let's go. So you might say that, see, the error was just 20, but because we're squaring it, it becomes almost 400. That's like crazy. So won't it just increase the error? But actually it wasn't the error. So what you do is you do a root mean square. So you take a root of this, so that the actual value kind of falls in the same line as the uh, unit of the, this unit. If you take the root of this, then what you get, this to 20, right? So that also helps. Cool. And we do a mean of them too. For what is the mean, basically? So this one was for one example, right? This one was just for this one example. Okay, this one example, but you are taking it for every single example, and you are adding all of them up and taking the mean. Okay, so basically, okay, give me a second. Okay. We're gonna go and see. Give me a second. Yes. Yeah. Hmm. So this is what we call a mean square error or root mean square error. We are not using root as of now in this equation, but uh, you can say you can use that root mean square error or mean square error. If you are taking the root, then only to say mean square error. Okay. So we're gonna deal with mean square error only. Okay, for our example as of now. So you have the equation would be something like this. MSE will be 1 by n. That is the number of examples that you have in your training data set. Summation of the error. Error is what? Y hat minus y, and you square them. So the I goes from 1 to n. Okay. So here the n is n where n is 100. Okay. If it's a training data set, it would be 80, right? N would be 80. So what you if you open this up, what you see is 1 by n is right there at the outside, and you take the y. Let's say the first example. What was the prediction of the first example? Square plus what was the prediction of the second example and the actual second, sorry for that, and the actual second example square. Then all of that, and what was the of the 80th example minus, sorry, the actual 80th example, right? I hope, oh, I hope this makes sense. And done. So this is what we call. So you have the prediction of, this is the y pred. This is the actual y train values for the first one. I'm gonna put first. Okay. This is how we are going to quantify uh, the error. Okay. I hope that makes sense. So that's what we are doing here. We are taking the error y hat minus y train. So just so you know, y hat and y train, if you see, they are 80 by, so if I'm not being clear, so it's 80 comma 1, and this dude is also 80 comma 1. So it's y hat and y train, right? So it's basically like a big column of 80 lines, 80 rows basically. Hmm? And when you do subtraction between them, it does element by subtraction. So this element will be subtracted with this one, and this one. So you get a error will be also an 80 comma 1 matrix. Okay. So we can also check that out. So I'm going to calculate the error here, and let's see what error looks like. So again, it's a simple matrix, 80 is to 1, 80 comma 1, sorry. And that's how it looks. And the loss will also have the same shape actually. Will it? No, of course. We are taking a scalar because we are doing the mean of it, the whole thing, right? So if you do the shape of that, it's nothing because it's a scalar, right? Okay. So we already printed the loss. That is the loss that we have is 2.74, and our goal is to reduce this loss. And hoping when we reduce this loss by changing the w and the b value, that is the intercept and the slope value, we can eventually get to a point where the loss is minimal or zero, ideally, uh, and we will be able to train the model, and we will get the values of w and b that actually uh, corresponds to the actual values that we initialized. That was the values here, basically 1 and 2, right? This one was the value, b is equals to 1 and w equals to 2. Okay, and our value right now is what? 0.49 and minus 0.1382. Okay, cool. Now let's calculate the gradients. So let's do this. It's pretty easy. Hmm? Okay, I'm gonna solve it here. A mathematical intuition. So you have this MSE, that is your loss, or you can call it the loss. Hmm? I know it was 1 by n summation of what? Y hat minus y. Hmm? Just so you know, I forgot to give this, I guess. Yeah. It's, as the I is here, right? So I will be here and here. Okay, so I is there and I comes in here and comes in here. Okay, that's all good. Let's open this up as well. Hmm? So if you have this I equals to 1 to n, and then, so what is y pred? Y pred is nothing but whatever is coming, that equation, right? This is the y pred. You're doing the front propagation, right? So I can write y pred as b plus wx minus y I. This is xi. Cool. And you to take the square of this whole thing. Okay. So why do I want it in this form is what we will be discussing. And the next thing, that is we are going to do gradient descent. So we are going to differentiate this equation in terms of the two parameters that we are going to train. That is, we're going to differentiate in terms with respect to b, and we are going to differentiate with respect to w. Okay. So let's do some gradient descent. Okay. Okay. So this whole value, the MSE, the loss value. So I can do loss and partial differentiating with B. Okay. Now, if you think, now if you see, the whole thing depends on what? We can break this whole thing down actually. Okay. B is there, right there, right? And I can directly do this 1 by n summation, whatever I am not writing the I part, it's understood. 2 will come out because it's a function, like b plus omega xi minus yi. Done. Coming back here. So you see now. And if you differentiate b with respect to b, then it's 1. The other things will be 0. So it will just be into 1. Okay. So if you see, this whole thing is what? It's nothing but y hat. So why don't just put that? And summation of 2 y hat minus yi. That's it. I here. Okay. Same goes with the loss function and w. Okay. Again, same thing. 1 by n. 2 comes here and w psi yi. If you differentiate the whole part, this becomes 0. This one will just leave out xi, and this part will be again 0, right? So we got xi out of there. Let's, again, this whole thing is what? Y hat. So 1 by n summation 2 yi hat. Sorry, 2. I should have written the 2 back there. Okay, whatever. And again, xi. So you got the values, you got all the things that you require for doing the gradient descent. So now you have the loss. Okay. Let me give you a little bit of geometrical intuition of what is happening. So if you think the error that we have, or the loss function that we have, the loss function is a parabola, right? It's a y hat minus y square and something like that, right? So it's basically a parabola like this. Okay. And what we want is to find we want to reduce the loss, right? The loss needs to be reduced. So if you see in this scenario, when is this whole function, this curve, the lowest here, right here at the end. So our idea is to basically find this one. so that we can find the last one, which is the lowest and the least value of loss. It need not be 0, okay, and it can be something very small. That's our whole point. Okay, so we are approximating this value. So when you start off with something, for example, in this scenario, we had the loss was 2 or something, right? If you remember, the loss was 2. Yeah, the loss is 2.7 something. Yeah, right here. So 2.7 here. We want slowly to go here on this direction. Slowly, we want to go in this direction. With every step of training, we want this to happen and eventually get to this point. It might not exactly converge at the exact end of the curve, but we want it to go slowly towards. We want it to slowly diverge here and come down here. Okay. So why is it called gradient descent? Actually, gradient in itself, if any call gradient, it always, if they have a curve like this, gradients will always point to the steepest slope, the steepest point in the whole thing. But we want the opposite. We don't want to go to the highest point. So this is what we call a gradient, right? This is your gradient. We want to do the opposite of that. We want to do gradient descent. We're going to go back. We're going to go down. Okay. For that, we will actually subtract it, but that's all good. We'll talk about it later. Okay, so you calculated the loss, and this is where the according to this equation, okay, if you see what was it, 2 into the error mean, so that is what is it is. If you take that 2 out, so that is what it is, right? 2 is outside, and then this 2 is outside. This whole thing looks exactly like error. Right, this is what, this is your error basically, and you take the mean of it. That's why we have the 1 by n. So that is there, and this is if you see this one again, I can rearrange this equation to look like 2 into what, xi into the error, basically the whole other thing that comes like this, 1 by 2 again, y hat y. Okay, everything comes in. That's what is happening here as well. I hope all that makes sense, right? So the xi is under summation. You remember that xi is under summation. That's why we took the multiplication of both of them and then did the mean outside. Okay, you see this mean is happening for this whole thing. Cool. And let's print out the grad. So gradients, gradient values is the one that we're going to use to update the parameter. That is, we're going to update w and b. So if I print it out, you get the values. So basically it's like saying I have the xi value, right? For, let's say, for the b one. So I had for this equation, see this equation, I have the actual predicted value. I have the value of the actual one, right? So, and I know what the n is. I can easily calculate the gradient. I could simply done that. So that's what happening here, and the calculation is done here. Same for w. I have xi, that is the actual value, x value, and the predicted value, and the actual y value. I have all the things that you need, so I can easily calculate the gradient differentiation, right? So you got two of these values, right? Cool. Uh, Let me just see if there's anyone. Okay, cool. Yeah, let's see. Now we are gonna update. Okay, so one thing you must have noticed, the gradient is negative. Here is also negative. Hmm. Now the loss was somewhere here. Okay, gradient we have to subtract from the actual value. As I said, gradient descent we want to go the opposite side. In normal gradients, it always points to the steeper side. So we want to go the opposite side. That's why we subtract it. So basically, the whole equation, the updation equation, seems something like this. B new will be equals to B old minus some learning rate, the loss, and divided by B. Same goes for W new equals to W old equals to this, and loss divided by W. Sorry, it's supposed to be a negative value. Yeah, this is what's happening. We subtract it from the actual value because we need it to go down. I hope that makes sense. Okay, cool. Uh, yeah. So now that we have this gradients, we can simply do that. Just create a learning rate. Learning rate basically telling you how fast you want the convergence to happen. If your learning rate is high, this convergence will be this convergence will be like big. Every single step will be like big steps. If it's small, then this step will be smaller. That's it. Okay. And there are problems with that too. I mean, if you put learning rate way too high, so what happens is sometimes instead of jump going here, it might even go away from this divergence. It can step over it and go right here somewhere. So one single step will land you here, and then the next step will land you here, and then again this can be a problem, and it will never converge. And if it's way too small also, then also it might just stay here and never converge. Converge is basically come to the least value of that loss function. Okay, so we are gonna update. So you see the actual value of B right here. Okay, this is the actual value of B and W. Okay, I guess this is not the value. Yes, this was the actual value. Remember, from the first, we initialize it randomly. We did initialize it somewhere here, right? Yeah. So these two values were the initial values that we had. Now we're gonna update it. So after one updation, you see that this is the value. Okay, of course, the B was supposed to be 1 and W was supposed to be 2. That was the from the actual data set that we had. B was supposed, the true value of B was 1 and the true value of W was 2. And this was the value that we had before. We are getting to that point, right? It's become the, of course, it's 0.8 now from 0.4, the B value, and this is from negative to positive value. Cool. Now we got the new value for B and W. Why don't we just go back and do the same thing over and again? Let's do from the step one. Basically, is the loop that we are creating. Okay. Now we are gonna calculate the y hat using W and B. Again, it goes in here, and now we have the updated value for the y hat, right? And again, we calculate the loss with the new values for B and W. You got a loss that is smaller because the loss that we had was 2.7, right? Now again, we go back and calculate the gradients. We find different gradients this time, and then update. So see now how the values change for B and W. Okay, we are almost there. B is already 1 now, and but the W isn't. So let's do it a few times. Okay, let's see if we can get to that point. Update. Okay, 0.3. Cool. Again, let's go through that again. Update. Okay, it's happening. It will take a lot of time, a lot of loops to do the same thing. So this is basically I'm showing you a loop just by actually running the cells over and over again. But what you can do is you can just create one big loop for the same thing. See, the first step is there, second step is there, third step, the fourth step, and then print out the value. So right now it's going to do the same thing for almost 1,000 steps. So those steps are what we call the epoch, right? We initialize some values here, we printed out that initial values and the learning rate and epochs. So if we do this, you see the actual the random value that we initialized for B and W was 0.4 and this, and it almost have converged to the value that we wanted, that is 1, and this is almost 2, right? 1.96. So this is a universal approximator, like deep learning in itself is a universal approximator. So we are able to approximate the values of actual true B value and true W value. Okay, so you can see I can just use so this is basically I'm using the linear regression uh, function from the scikit-learn library and doing just fitting it on my X-train and Y-train and seeing what my B and W values are. And they seem to be very similar. They are exactly same because of course there's gonna be some difference, and the way scikit-learn implements the whole thing, the initial values might be different, the initial B and W values might be different, or there might be some other optimization they do. So but you can see both the values are almost same to oh my god, that's like six numbers after the decimal point. That's pretty cool, right? Yeah, so we checked it out and we see this is the model that we got out of it, the graph that we got out of it. This is the prediction that we did. So B is equals to this and W is equals to this. It's almost, you can see it's this line actually fits the data. Cool. We're gonna do the same thing using PyTorch. Okay, so I hope this much is done. I don't wanna uh, spend more time on this one. So let's see what we can do about it in the next live. Okay, so this is it for today.